So, welcome to this lecture. Today we will see broadside array. Now, what is a broadside array? When the progressive phase shift we make 0, that is the broadside array. So, that means no progressive phase shift between elements. So, all elements are fade in phase. So, the moment we do this, we are getting u0 is equal to 0. So, if we look at the diagram, the major lobe is immediately u0 becomes 0 means major lobe comes here. So, major lobe maxima at u max is 0. So, cos psi max is 0. So, psi max is pi by 2. So, it is proved that the maximum radiation occurs broadside to the array axis. Physically also this is expected, as all elements fade in phase should be producing maximum radiation along the broadside. Now, grating lobes are plus minus 2 pi away from the main lobe at u is equal to 0. So, you see that if the main lobe comes here, so I have a k naught d here, I have a minus k naught d here. So, if I want to put that even if the grating lobe starts appearing here, there is no problem. So, if we keep d equal to lambda naught, actually slightly less than lambda naught, just d is, I should not say equal, d is equal to less than lambda naught, the grating lobe gets avoided. So, the visible regions become minus 2 pi less than u less than 2 pi, provided d is less than lambda d. So, you can make that for broadside arrays, you can say that inter element spacing is equal to lambda naught. So, we have already seen that main lobe null occurs at null, major lobe we have seen now, main lobe null. We have generally seen that n by 2 u plus u naught is equal to plus minus pi, but for broadside u naught is 0. So, in this case u naught is 0. So, let us find out. So, can I say that cos phi, you put the value of psi, so you get cos psi is plus minus 2 pi by n plus 1 k naught d, which is plus minus lambda naught by n plus 1 d. For n large, cos psi value will be very small. So, we can say that psi is equal to pi by 2 plus minus delta psi. Can I say this? You see that n large. So, cos psi is small. It is not 0, but very near 0. So, psi is pi by 2 plus minus something in both sides. So, we can write cos psi is cos pi by 2 plus minus delta psi. This is small, that is why I am writing delta psi. So, this is plus minus sin delta psi, that means delta psi. So, I got the value of delta psi. Now, what is the beam width? This is the null. U is equal to 0 is my main beam, this is one side plus delta psi. So, beam width is 2 delta psi, and that is 2. What is the value of delta psi? Previously I have found value. So, 2 lambda naught n plus 1 into d is equal to 2 lambda naught by L. What is L? The length of the array. L is array length. L is equal to n plus 1 into d. So, this is a general property of a broadside array, that the beam width is inversely proportional to the array length in wavelengths or array's electrical length. So, for a beam width of 6 degree, an array of L by lambda naught is equal to 20 is required. And if lambda naught, if d is almost equal lambda naught, you can say 20 element array is required. So, as an antenna designer, specification given what is the beam width required, null to null beam width, you can easily find out how many elements are required. At high frequency, this is quite feasible, 6 degree thing, but at 1 megahertz, this will require an array length of 6 kilometer. So, that is why this array antennas for broadcasting is not so popular. You see, this is a 1 megahertz is a broadcasting thing. So, broadcasting people generally take only a single antenna, dipole or monopole basically, with a huge tower. For normal communication it is impractical, but for weather radar or research system for extraterrestrial observations, looking at distant stars, this type of arrays are made. So, array pattern is like this for broadside array, and this was the half wave dipole pattern. So, if you do resultant pattern obtained by pattern multiplication, so here side lobes are not shown, but with the array of dipoles, broadside dipoles, you get a pattern something like this, where arrays are x is the array axis, you get the pattern. This is much smaller, beam width is much smaller than the thing. This is in fact that will come later. Okay. Now, if we want to estimate the directivity, it is difficult. For half wave dipole, you see that actually the way we defined directivity for antennas, there we will have to have an integral something like this. we will have to evaluate this. Why this? This is actually dipole's pattern. You see, I have taken square of that. This is the broadside array factor. Now, this is difficult. Instead, what we do, we approximate D by like this. You see, if you remember the basic definition of directivity, then I can say what is it? It is the 4 pi is the total solid angle for the isotropic radiator divided by solid angle occupied by main beam. This is an approximate definition, but approximately my antenna's main beam, the solid angle it occupies, if that is in the denominator, and 4 pi is the solid angle occupied by the isotropic radiator. So, this should approximately give you the same thing, though I again caution that actual thing is from their intensity of radiation and the power radiated, etc. That is the actual expression. So, here again I can approximate this, that 4 pi divided by principal you see solid angle occupied by main beam. Now, why we came, and actually you see our this this is the array pattern. So, this is figure of revolution about x axis, that means this has improved, you see our azimuthal pattern. Now, what we said that generally the job of array is to change the azimuthal pattern, and we are using dipoles. So, can I say that principal E plane half power beam width into principal H plane half power beam width. This will be the solid angle occupied by the thing approximately. Now, for the array we have shown approximately we can say that principal E plane half power beam width is same as the dipole's principal E plane half power beam width. So, that means what is this value for dipole? This is 78 degree or 1.36 radian, and this will be given by this H plane pattern, this is given by array. Okay. So, this will come from array factor. Now, this is half power beam width, we have calculated null to null beam width, that won't do. So, we will have to calculate the half power beam width from our array factor. So, please note that at 3 dB points the array pattern will be, what is the value of the array pattern f, that will be n plus 1 I naught by root 2, because peak was n plus 1 I naught. So, it will be n plus 1 I by root 2. Now, already we have seen that Fu is I naught sin n plus 1 by 2 u plus u naught I am not writing by sin u by 2. So, we can put this value n plus 1 I naught by this, and then we can write sine square n plus 1 by 2, and this angle we are calling u half is equal to half sine square u half by 2 n plus 1 whole square. Now, u half is very near to u is equal to 0. So, u half is small, and its variation is much slower than n plus 1 u half. So, we can write that this is approximately half u half by 2 square n plus 1 square. That means, here I can replace this u half, and we can expand this sine function sine n plus 1 by 2 u as n plus 1 by 2 u minus in the series expansion of sine. So, you can put this that n plus 1 whole square by 2 square u half square 1 minus 1 by 6 n plus 1 whole square by 2 square u half square is equal to n plus 1 whole square by 2 square u half square by 2. So, if you solve this, you will get 2.65 by n plus 1. Okay. So, note down this, do this, it comes, I have done it myself. So, but what is u half? Is k naught d cos pi by 2 minus delta, and this is k naught d. So, half power beam width is 2.6 into 2 by n plus 1 k naught d, 2.65 lambda naught by n plus 1 pi d. So, ultimately we got the H plane beam width is this. So, we can put it into the directivity, that will be 4 pi by 2 into 1.36 into width half, and that will be 5.48 n plus 1 d by lambda naught. Okay. So, this is the expression of directivity for an uniform broadside array. So, for example, suppose 20 element and d is 0.9 lambda naught. You will see that this array antennas beam width, that if you do, it will come as 0.045 radian, and if you put that into the directivity, it will be something like 103, which is 20.1 dB. So, a 20 element array has a very substantial directivity and also large gain, as losses due to array antenna there is not much loss. So, obviously there will be some losses, but you see you can make almost the gain was multiplied almost, I can say how much, that typically the for an dipole array it was 1 or 1.5. So, 60-70 times the 20 element array has multiplied these. This is a very sizable factor, and in very sophisticated applications also this can do in radars, etc. This gives a very good antenna, array antenna. So, we can compare that if the array elements are isotropic radiators instead of half wave dipoles, then the pattern will be a circle about array axis. Array will have this thing. So, what will be if you do that, instead of dipole, if I give the isotropic radiators, so in that case bandwidth in E plane, since isotropic, so in E plane it does not have any bandwidth. So, we will take bandwidth in E plane is 2 pi, because it will be like a circle in the E plane also. So, beam width is 2 pi. So, we can say D will be 4 pi by 2 pi into whatever is the array's bandwidth, beam width. So, this will become 2.37 n plus 1 d by lambda naught. So, you see substantially you can put those values again, that n is equal to 20 and d is equal to 0.9 lambda naught. So, this becomes 2.37 into 21 into 0.9. So, I think that is something like 50 or something. So, something like 50 I can say. So, you see that compared to 100 I have 50 half. So, not bad. That means I actually, that is why in array antenna the main contribution comes from the array factor. So, you can put any antenna. There actually obviously a dipole will be preferred over isotropic radiator in the sense that you will have to have the power handling capability and other things. So, any type of practical antennas will do. We will see later that actually in real life this where antennas actually they get protruded. Instead, if array is on a ground plane and then the open ended waveguides flush to that ground plane, that is much preferred, because then only the one front surface comes of the array antenna. So, array antennas with open ended waveguides is a very good choice, because the open ended waveguides can handle sizable amount of power, and even if they are not good radiators like dipole, but for array antenna they are ideal candidate. That is why in missile guidance systems or radars, etc., these open ended waveguides are very preferred. Actually, we will see when we will, that is why open ended waveguide antenna we will see that as an antenna element for array antenna, this is quite good. With this I conclude the broadside array, and in the next class we will find end fire array, and then we will see some parasitic array, particularly one array which is very popular as a TV antenna, was very popular, that is Yagi Uda antenna. That also is a good example of antenna. that how array antenna can improve the performance. Thank you.